Welcome back, literature fans. It's been a while. Today we're going to cover binomial expansion. It's going to be a slug festival. Okay, get ready. But we want to be familiar with these binomial expansions, and that's always a good exercise. So let's get to it. Here's our famous triangle from Pascal that's used for binomial expansion, and the formula for these particular factors, well, it's I think it was given by, is it Newton? It's hundreds of years old, and it looks something like this. So here I got it for, I'm going to do n equals 6, this line here, right? N equals 6. So we want these factors here. 1, 6, 15, 20, 15, 6, 1. You see how they go? They add. See, these two add. These add, and it just keeps working like that. But there's also a formula for that, for these factors, and that formula is given like this. You've got n, and then the n keeps dropping by 1 on the top side, on the numerator. On the denominator, it's really a factorial, you know. Over 1 times 2, that's 2 factorial. 1, 2, 3, that's 3 factorial. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So let's crank it for n equals 6, and let's see if it gives us these factors. So the first one, well, that's 1, so that's that one. And if you plug in n equals 6, well, you get 6 right away. Okay, no problem. And then what do we have here? We got 6 times 5, right? 6 times n minus 1 over 2. Well, that's 3 times 5 is 15. That's this guy. All right. Next, 6 times 5 times 4 over 2 times 3. 2 times 3 is 6. So that's 20, right? Well, that's this factor right there. Next factor, this one here. 6 times 5 times 4 times 3 over 2 times 3 times 4, right? Well, that's these. And this is 3 times 5 is 15. That checks out. Next factor. 6 times 5 times 4 times 3 times 2 all over 2 times 3 times 4 times 5. Wow, look at that. That just cancels out and you get your 6. And finally, 6 times 5 times 4 times 3 times 2 times 1 all over, what? 2 times 3 times 4 times 5 times 6. 6 factorial. Well, that just completely cancels out. You get 1. And there we have it. Pretty simple, huh? Try this for other factors. Try this for n equals 5. Try it for bigger factors, n equals 7. That's your assignment. Okay, so we're going to be using this in our next example. That's the whole idea. I want to be comfortable with this. You know, using these expansions, because we use binomial expansions a lot. And that's the whole goal of get used to it. So, continuing our binomial expansion Slug Fest, we are going to, basically we're going to find our k sub n factor for, well, general purpose k sub n for n equals anything, given that we know k0 is 1, k1 is 1/2, k2 is 1/3, k3 is 1/4. These are the normalized invariant ratiometric factors for a constant, a linear term, a quadratic term, and a cubic term. Okay, and go back to my previous videos. We've got these kind of using a layered approach, starting with, well, these smaller terms. And we're going to use basic setup. I call this the Wildberger setup. He uses translation of t equals 1. X equals 1 plus t. And so this is what we're going to have. Here's our x-axis from 0 to 1, 1 plus c. Our translation axis, t-axis, is going to be -1, 0, c. See how it's offset? It's offset by t. When t equals c, well, x is equal to 1 plus c. That's how you get it. You see that? You able to follow? No problem. And so y is equal to x to the n, where n could be anything. You know, it's some huge astronomical number. And so with translation, you plug this in, 1 plus t to the n. See that x? That's where it goes. Okay? And so here's where you need the binomial expansion. You're expanding these two terms to a power. And that's binomial expansion. This is where we're going to use our formula that we had previously. And so, okay, let's expand this. These would be a linear term right here. No, a constant term, a linear term, a quadratic term, a cubic term, and so forth, all the way up to t to the n. Constant, linear, quadratic, second order, third order is cubic, dot, 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 t to the n. And so the formula is, and this is the formula for these various factors, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so forth. These factors here, these are the binomial factors. That formula is, okay, it's 1. It's going to be n over 1, of course, times t. n minus 1 over 1 times 2, or 2 factorial, times t squared. n minus 1, n minus 2 over 3 factorial, times t to the third, and so forth, all the way up to tn. And that's these little functions in terms of t, from the t perspective, that builds up this funny looking wedge over here. See that? Constant, linear, and there's quadratic, cubic, and so forth. And these are various heights that are determined by the binomial expansion. See this? They're different for different n. And, okay, so we said that we're given k0, k1, k2, and k3. That means that we can take it easily up to t squared, t to the third. So let's do it. The area of this wedge right here, this big wedge, from the t perspective, this little one, and we'll include this one shortly, but right now I'm focusing on these areas here. K0 times the box of this thing. Well, that's, you know, and here's K1, which is your 1/2 factor, times whatever height this thing is. See that? And then you got K2. That'll be the height of your second order equation. That'll be right here. And so on. And the base is always C. So let's crank it. All right. Area. Area from the x perspective. Area. It will be K sub n times this whole big wedge, right? Well, that's really 1 plus c to the n times 1 plus c. You see that? 1 plus c to the n times 1 plus c. Well, you might as well write it n plus 1, because that's what that is. Okay? That's from the x perspective, this big wedge. And that equals, we got to pick up this little area, and then we're going to pick up these areas right here. Okay? What's this area here? Well, that's K sub n times base times height. That's just 1, right? This is 1 by 1. Simple. Plus. Okay. Now we got to pick up this one. This is right here. Well, that's just a rectangle, so that'll be 1 times C. Always C. See, 1. That's your height, and base is always C. That's simple. That's our K0 factor, right? That's the 1. Plus, let's see what else we have. We got, oh, well, we got 1/2, yeah. 1/2, because that's our K1, times the box of this thing. Well, that's NC, that's its height. You plug in T equals C. And then don't forget your base times C. Okay? So that'll be the area of our linear function here, right here. Plus, the quadratic is going to give us 1/3, which is our K2, right? Times n minus 1 over 1 times 2. Okay, times c squared times c. Right? C squared comes, you plug in t equals c, and then the base, so everything is always this base. It's base times height, or height times base. Plus, we're going to do our cubic. Cubic is going to be 1/4, right? K3, which we already know, times n minus 1, n minus 2. See how it's decreasing here? And then the factorial is increasing. 1 times 2 times 3. Whew. No wonder I'm calling it a Binomial Expansion of Slug Fest. Okay, plus a whole bunch of stuff, plus finally k sub n times c sub n, c to the n times c. Whew. Okay, I gotta check my notes because, oh boy, it's easy to make a mistake. I think it's right. Okay. So here we have it. From the x perspective, the big wedge is equal to, don't forget this little guy, k sub n, and then we got these like that, these little subfunctions. Okay, so we have to expand this. This is another binomial expansion. Whew. No wonder I'm calling it a slug fest. Okay, let's slug it out. Crank. K sub n. Whew. 1 plus, it's going to be n plus 1 times c. Whew. Is that right? Yeah. Plus n plus 1 n. This will be c over 1, right? 1 times 2, 2 factorial, and this will be c squared. Plus, keep going. How much do we need to go? We'll take it up one more time. N plus 1, n minus 1 over 1 times 2 times 3 times 4. Ooh, is that right? Yeah. Oh, something's wrong here. Times 3. Aha, that's right. Okay. 3 factorial times c to the third plus, whew, n plus 1, n minus 1, n minus 2, oh boy, 1, 2, 3, 4, and this is c to the fourth, and that equals everything over here, which equals, oh boy, let's kind of simplify. Okay. Whoa, 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 plus, dot, dot, dot. And the last one is c to the n plus 1. Don't forget that one. Yeah. That's right. Checking my notes. Okay. Whew. Some things are going to cancel. And you've seen that in my previous videos where I did a simpler thing, but it's always the bookends, right? K sub n times 1, really, this one cancels this one. Bye! And the other side, k sub n times c to the n plus 1, that'll be this one. That's gone. So all that we are left with are c terms, c squared terms, c to the third terms, c to the fourth terms. Whoa! C. I forgot that. And etc. so forth and so on. So let's see what happens. So we just collect our c terms, our c squared terms, each according to its kind, right? So let's do it. K sub n n plus 1 times c equals, this side has it to equal c on this side, 1c. Well, look at that. The c cancels the c, and all you're left with is k sub n equals 1 over n plus 1, which is Cavaliere's finding, right? That's it. Simple. 1 over n plus 1. That's great. We found it. But what about these c squared terms? Let's see what happens. That'll be these two, right? So we have k sub n, n plus 1, n over 2c squared equals, on this side, it'll be n over 2, right? N over 2c squared. Well, look at this. nc squared over 2, nc squared over 2. That cancels out. And what have you got left? Well, same thing that you had before. Solve it and you get k sub n equals 1 over n plus 1. Same thing, redundant information. These simply cancel out. And you got the same thing as you did before. So you don't need the c squareds. It doesn't give you anything new. But let's see, what happens if we want the c to the third terms, right? That'll be these, okay? K sub n plus 1, n minus 1, all over 2 times 3, c to the third, that equals, here's a c to the third, n minus 1 over 3 times 2, right? There's 1/3 and there's 2, and then c third. C third. Well, look at that. This cancels. These cancel. And what have you got? K sub n equals 1 over n plus 1. Redundant information. Let's keep going. C to the fourth term, right? I told you it was a binomial expansion slug fest. So let's slug it out. Okay. K sub n, n plus 1, n minus 1, n minus 2, the whole thing over 2 times 3 times 4, c to the fourth, that equals, let's look over here, yes. Okay, n minus 1 minus 2 all over 4 times 2 times 3, that's c to the fourth. So look at what happens. The bottom, that cancels out. And on the top, everything else, gone! There it is. Giving us k sub n equals 1 over n plus 1. Redundant information, but that's the way it is. So there you have it. Welcome back, Quadrature fans. Okay, so last time we were doing Binomial Expansion Slug Fest, and we basically did it for the area. Today we're going to finish it. We're going to do it for the slope. And for the slope, we're also given C0 equals 0, C1 equals 1, C2 equals 2, C3 equals 3, and we want to find out what C sub n equals, right? These were given in my previous lecture. We arrived at these numbers. So kind of keep this in mind. There's a great similarity between the area and the slope from the algebraic perspective. I need some room here. I'm going to wipe this out, but you can see here, just to refresh you, that we have basically redundant terms. We found k sub n is 1 over n plus 1. Okay, so we'll proceed in a similar way for our slope. And this is slope, tangent slope at, well, at t equals c, or x equals 1 plus c. That would be the tangent slope at point Q, let's say. And that's this one here. You see that? That's what I'm talking about. That tangent slope from the t perspective, well, that equals, well, we know that these are individual functions. There's the constant, linear, quadratic, cubic, etc. up to t to the n. So let's see, C0 times the diagonal of 0 plus C1 times the diagonal of this thing, the linear term, plus C2 times the diagonal, the quadratic term, plus C3 times the diagonal of the cubic term, plus dot dot dot, plus C sub n times the diagonal of the last term that we have here. You can kind of see a very much similarity between the way the area works and the way the slope works. These are basically your box operators on these functions right here. And the coefficients, well, they're determined by this formula. That's why we call it a Slug Fest, because there's a lot of them. But, okay, slope. Tangent slope. From the x perspective, at x equals 1 plus c, that would be c sub n times rise over run, which is the, guess what? That's our diagonal, right? So it's c sub n times this diagonal. That's what we're saying. That's an invariant property that we have found and proven using rubber band geometry. So let's do it. So it's 1 plus c to the n, divided by 1 plus c, right? That's on this side. Well, you can rewrite that as 1 plus c to the n minus 1. See it? And you can see the similarity between the area and the slope. With the area, basically it raises by 1 power. With the slope, it lowers by 1 power. That's algebraically, that's the difference between them, right? Pretty cool. So this is from the x perspective. From the t perspective, we've got these individual functions, and they each contribute some kind of a slope, especially at t equals c. At t equals 0, the only function that contributes slope is the linear function. We've shown this, so it's really easy to get that. But I want to proceed with t equals c just to see that similarity. Yeah, we're doing a binomial expansion slug fest, so let's slug it out, okay? So now from the t perspective, Well, let's just do it. It's C0 is always 0. That's, you lose a term. That's easy. That's goodbye. Then our linear term, C1, which is 1, times, well, what's the, what would that be? T equals C will be N, C, rise. That's this rise here over run. The run is always C divided by C. So you can see that it's N. That's right, that's the slope. That's pretty easy. That's the linear term. But I like to draw it this way. Okay. Plus, the quadratic term, we need our C2 factor. We're doing this. C2 is really 2, which we already know, times, and the binomial coefficient is n minus 1 over 2 times C squared, rise over run. Run is always C. Okay. Now our cubic term, is that right? Checking my notes. I think that's correct. No, I don't think we need any more. I think we're good with this. We don't need any more terms. C squared, C third, if we do, I'll put it in there, but I don't think we need it. Well, except for the end, plus the very last term is C sub n times C to the n divided by C. And remember, this C sub n and this C to the n are different variables. Don't get those mixed up. I've already talked about that before. So this is a C and this C, these C's are different. Okay, I think we're good with this one. Yeah. Well, let me take it further. I think there's one more. So 3, we'll do this one, the cubic, 3 times n minus 1, n minus 2 over 2 times 3, C third over C. Rise over run. Okay, well, all right, let's put that in. So that's from the T perspective. Let's go back to the X perspective. We've got to expand this out, right? That's just another binomial expansion. So let's do it. C sub n times 1 plus n minus 1 times C. Yeah, I'm checking. Okay. Plus n minus 1, n minus 2 over 2. This is over 1 factorial. And this is over 2 factorial. Yeah, C squared plus plus C to the n minus 1. Is that right? Yes. The last term is a C to the n minus 1. Whew. Okay. Basically, there's going to be something here that cancels out. And that'll be C sub n times C to the n minus 1. Right? Maybe I should... Now let me rewrite this from the T perspective. Equals nc plus, well, 2 cancels 2, so you got n minus 1, and this becomes, not nc, just n. This becomes c squared over c, so that becomes a c plus, the 3 cancels here, so we got n minus 1, n minus 2 over 2, yeah. And c third over 3, that's c squared plus, at the very end we got c sub n, c to the n minus 1. Okay, I think this is a little bit cleaner. So things that cancel out, c sub n times c to the n minus 1. This one cancels. Alright. And what's left? Well, we got our, you could call this the c to the 0 term, c to the 1 term, c to the, I forgot, c squared times c squared, and go on, so on, and so forth. So let's collect the terms. We're going to collect these terms, separate them out, and here they are. C sub n times 1 equals what? Equals n. That was pretty simple. C sub n is equal to n. That was really simple. We kind of knew that. But there it is. C sub n equals n. Just from these two. Oh, let's collect our c terms. C sub n minus 1 times c equals, on this side, so where's the c term here? n minus 1c. n minus 1c. Okay. Well, guess what? This cancels this. C sub n is equal to n. C sub n equals n. Again, this is redundant information, but you see the similarity already with the way we did the area. It's just one more. C squared with a c squared. Okay, so c sub n, n minus 1, n minus 2 over 2 c squared equals, on this side it's n minus 1, n minus 2 over 2 c squared. Well, guess what? Everything cancels out except this n. There you see it. The 2 cancels out. So you're left with this n. C sub n is equal to n. Redundant information. Similar structure to what we've had for area. And even just take a look at digest this thing, particularly right here from the x perspective. Here we see area of this big wedge is simply that 1 plus c to the n times 1 plus c. So it's 1 plus c to the n plus 1 raised by 1 power. Here the slope, tangent slope at point 1 plus c from the x perspective, or t equals c, from the x perspective it's c sub n times 1 plus c to the n minus 1, because we have to rise divided by run, so it lowers by 1 degree. And look at the similarity here is striking. I mean, one raises, the other lowers. Different ratio factors, but the math cranks the same way. It's if you've done it for area, you can do it for slope, tangent slope, and you see similar redundancies happen. You can throw them out. So what have we learned? Basically, we didn't need to do this binomial Slug Fest. Why not? Because these terms here in the area, they're redundant. So you only needed to take it to that one, expand just the first ones right here. You got it. And similar with our tangent slope, you really didn't need to do all this heavy work. Just a couple of terms and you got it. You know, it's so simple. But you know, it's good to do binomial expansions and just to be familiar with it, comfortable with it. You know, that's the key. That's the whole purpose of doing it. Just kind of as an exercise, and it reinforces that yeah, we're getting redundant information. At least it's not conflicting. C sub n is n. C sub n is n. That's good. And so on and so forth. So remember, before there was calculus,
there was quadrature.
All right.